Hi everyone. So I'm David. The thesis topic for today, the future of control, and here is the central question that we're trying to answer: how can we make control systems powerful and flexible for modern productions? So I've struggled before when presenting about this, like what I describe as control systems. Uh, if sometimes I use the word show control, like that tends to mean different things to different people in different segments of the industry. But just to kind of clarify, the specific area I'm talking about is this kind of acronym soup of technologies. So we're mostly focused on like what I would call like real-time control. So devices that are sending data to each other to indicate what they should be doing right now, rather than about like management or configuration of devices, which I think is a slightly different topic. Um, Natural responsive, most people, when I ask them to say what the issue is with the current ways we do control, is what's wrong with the way we do things now? Here's my kind of laundry list. Currently, the things we have they're slow to set up and configure. They're inflexible. They require reconfiguration to cope with changes in production requirements. They're inaccurate. They put demands on the way we represent data and information and move it around, and also the ability to deliver that with the kind of timing requirements that we increasingly want. And my spell check of the term timing isn't a word. But yeah, they're easy to misconfigure. They rely on users putting in the right addresses, settings, and also in multiple places. It's really easy to like just kind of just get an address wrong, get a magic string wrong, and suddenly your system doesn't work, and you have no way of diagnosing that without walking between lots of different machines or opening different bits of software. So overall, I'd say our systems that we use right now are kind of outmoded. And why is that? Well, uh, we're in the industry. I think we're very good at creating what I call as like the permanent temporary solution, because we're good at adopting technologies that are not built for us and then using them to meet the kind of needs that we have. We design our processes around the kind of limitations of the systems that we use. But today, I want to talk about like what could we do if we didn't have to do that? If we could design a system that was actually what we needed and is designed explicitly for the requirements we have, what could it be like? So let's kind of try and do a bit of blue sky thinking, and I'm going to present to you like my ideas for the problems we have with existing solutions and how we could address that in a new technology. But also like, why is this important? Because the control technology we use defines the way we interface to systems, and consequently the way those systems are structured. So for example, like DMX-based media servers, like generally kind of going out of vogue a bit, but that used to be the basic way that we controlled video systems in live entertainment. We had like all the programming was done in real time from a lighting desk control, and that put like actual, quite serious limitations on the way that the media server had to be represented, because it meant we had to have fixed layer counts, we had to have fixed capabilities. We could only have like 2 FX engines because we had to reserve the DMX channels for exactly that amount of parameters. But that was not a restriction of the software of the media server itself. It was a restriction of the way we controlled it. So, like, why are we letting the control protocols we use, the language which we use to address the system, define what the system is? I think we've got that bit backwards. So, like, in a new technology, we can think about how we can address that. Like, to temper expectations, I don't think that anything I'm going to describe is fundamentally going to make something that is currently impossible possible, because most of this is really about efficiency. The amount of time we kind of lose to these things, I think, is considerable. And whilst you could consider that just a cost saving, I think it's more interesting than that, because, as we know, time is money, and lost time is lost creativity. The more time we spend debugging systems, and the more time it takes to set up things that we might want to try from a creative perspective, then the less likely we are to try and do those things, and the less experiments we can do, and the more kind of communication has to happen between departments, between different devices, between manufacturers and software producers. And If we can just improve the way that we can communicate between devices, we can get that time back and we can spend it on doing the thing that actually matters, which is working on the project we're interested in. So, like an example of from something I've worked on previously. This is an opera called Breaking the Waves. I was a video programmer and system designer on this. We've got a projection map set on a revolve here. And what we're able to do is quite an interesting effect whereby we project the back face of the content onto the front of it so we can make it appear transparent. So these are like solid wooden columns. We can do this kind of transparency effect. Now this was like an incredibly low budget production, and I think we had like, being an opera, we had like 3 days of tech time. We were running to keep up with rehearsals. But when we first previewed this effect, the entire creative team were like just flabbergasted because it looked so convincing. Genuinely, like you can see when it goes around here, the people on the other side who were previously completely hidden. And the rest of the creative team said to us, like, are we the first people in the world to do this? And I said, well, no, but we are probably the first people to do it on a video budget of under 10K and in 3 days. So what I mean by this is that it's not necessarily the ability of our technology to do things that makes them interesting. It's the ability to do it quickly, efficiently, and cheaply that makes new creative possibilities possible. Okay. So just a little bit on my background as well. I started my career at Green Hippo. Thanks, Paul. I was part of the special projects team there. A lot of the work I did was in control protocols, and I wrote like a lot of the show control interfaces that Hippo uses. Um, uh, Supporting like client projects, often those then got turned into features of the product. I've also worked as part of Lux Machina, and as a freelance video programmer and system designer with my own company, Pixper. I've worked on projects in theatre, opera, touring, film, broadcast, live events, etc. And I also do a lot of software, custom software integration, and now it's kind of what I'm mainly doing in my role as part of Seismic. Also originally acquired by 180 Studios. And so I'm spending a lot of time at the moment developing show control products and thinking about how we can solve some of these problems and how we can develop new technology to address this area. So let's start off. What do we want from a next generation control network? So I've got a few categories. The first one being on the topic of flexibility. So first thing, we want our control network to be discipline agnostic. So we don't want a video control network, we don't want an audio control network, we don't want a lighting control network, we just want a control network because the types of data we're trying to move around in every case are the same. It doesn't matter what the end target is, we need something that can address all of those. So we shouldn't be optimized for any one type of data. We need to support all kinds of possibilities. Few of the currently used protocols are truly discipline specific, but they're definitely kind of like application specific. So DMX is like, you know, frame-based stateful control. MIDI's more kind of musical control. Posi StageNet for like tracking and automation data. I mean, you could repurpose these things for lots of other any way of transporting data, but they're generally, their limitations are set around a particular use case. So the kind of specificity there makes the systems overall quite complex because we can't use a single technology to connect everything without creating individually configured links. So our control networks currently look like this. We've got a bunch of nodes, we've got the different colors representing different kind of languages that we're using to talk from places. Everything's like point to point and like this is like a bit of a management nightmare, to be honest. You can kind of visualize it and you have to, but there's a lot of planning that needs to go into it. You need to decide where your links are. It's overall, it's quite fragile and it's quite brittle. So I think where we want to be is here. And now we've got an actual network. And this is, if you think about like other kind of paradigm shifts in the industry, especially things like 2110, this is where everything's going. We centralize the communication. We can talk to anything from anywhere. We're not creating point-to-point links, we're creating a network. So that's the thing, what we need to think about it as. So the advantages of this, we don't have to replan our control network when requirements change. Any one of these nodes can talk to any other. We don't need to create new connections. It still gives us the ability to like do things like segregation, so say for different departments. If they want, like this point does not, these don't all have to be the same Ethernet links. These could be isolated VLANs, but the point is we have a node in the middle that connects to all of them. And that's the thing that enables the kind of cross departmental collaboration. Okay, so next point, we want to be able to work on low-level devices and complex devices, software and hardware. If we want to truly unify and control technology, it has to work on everything, all scales of devices. And also needs to be properly bidirectional. So many of our protocols are not this. If you want to do bidirectionality, you have to send it in both directions that are completely unaware of each other. We want something that actually talks in both directions and it negotiates that in real time. Okay, next topic, discoverability. Devices should be able to find each other on a local network. This is an existing technology, MDNS, NDI uses it, lots of other kind of newer systems use it. It's a real no-brainer. It means that we don't have to depend on IP addresses anymore, which means because we don't have to depend on IP addresses, we can not base our communication and connections around IP addresses because it's actually not a very good way to do it. We are very set generally on statically addressing things. Which is like if you talk to anyone in the wider IT industry, they find quite strange. Because why do we care about like a device having a specific address? We have to care because that's how we determine what the connections are. But if we can discover things and discover their IP addresses, we can then instead use like a more of a unique identifier as be the point that identifies what that device is. So we can create connections which aren't based on connecting to an IP address, but are connecting onto an identifier, whatever IP it happens to be on. Which means that we can use things like DHCP, because the IP address doesn't matter anymore. Okay. So it also lets us have think about like things like dynamic clouding devices. So say you wanted to be able to bridge a whole network of like audience mobile phones or something to your control network, where you're never going to know what IP addresses all of them have, and you can't assign them static IPs. Now you can see them as they pop up on the control network, and each one will have a unique identifier, which even if its IP changes, will come back as the same identifier. You've got a point of reference for what your devices are. Okay, so if we find the devices dynamically, how can we do stuff that's useful with them? The devices have to be able to describe their capabilities to the control network. So this is how we create like a network which is actually self-documenting, where the device knows what resources it has and can report to the rest of the network what those resources are. This means we don't have to have manual standards documents, and it also means things can be dynamic. A device can change its requirements and report to the network that they have changed. And this can describe its capabilities, the kinds of data it can send and receive, what the state is, imperative triggers, things like that, what the valid and invalid values are for all of these parameters. So essentially, it's like kind of, it eliminates the needs for things like kind of fixture personalities or profiles from a lighting sense. It means that we can, we don't have to know about the device in advance in order to control it. Finally, double handling of configuration. What I mean by this is, as I described at the beginning, we don't want to have to walk between devices to enter the same information. That's where the errors come from. We don't want to have to maintain massive Google Sheets of all the addresses we're going to use. It's unnecessary. Like we've got a network that can discover everything on the network that exists, and we have unique identifiers. We can connect to something, select the connection via a drop-down list in a piece of software, and just remember what that connection is with no addresses required. Okay, so next topic, reliability. So first of all, the system needs to be connection-based. What I mean by this is that we need the idea of two devices having a network connection together needs to be completely independent of the data they are sending to each other, so that we can actually know whether a device is connected or is not connected to the control network. So this is kind of the idea of like we need a sort of a management plane, essentially. We need something to keep track of the connection state of devices and their statuses that is not responsible for sending any data. So the second you connect a device to the control network, we can sense its presence, we can get back all the information, discoverability, the metadata, what device it has, before it ever is responsible for sending or receiving any data to anywhere else on the network. So the issue with this is like there is an overhead involved in having a connection-based system. So for example, like most network protocols are based on either TCP or UDP. TCP is a connection-based protocol. You know when a TCP connection is disconnected. UDP, however, you don't know, and you don't know if anything's ever received the packet. But the advantage of using UDP is because there's no connection layer, the connection's very fast. The TCP has an inherent delay in terms of the negotiation it has to do in order to send data. So by using UDP, you cut that. So we can actually, by having both of these layers, we can get the both reliable and unreliable transports, TCP being a reliable transport and UDP being the unreliable. We can get the best of both worlds. We have a reliable transport for things that we have to know have arrived and for the management plane, and we have an unreliable transport for where the speed of data traversing the network is of the utmost importance, or where things that are going to update so frequently that if we miss a packet, it doesn't particularly matter in terms of the stability of the system. And finally, for reliability, we need native support for a failover concept. Now, if because we're not using IP addresses as our identifiers anymore, we can start to think about like putting devices in groups of failover. So we can we could connect a device to the network and nominate that it is the failover for another device. The system can understand this, and it can know, because we can monitor the connection state of the devices, we can automatically route it in and control the connections to it, or forward the connections to it from another device if it fails, because we'll know the second the other device has gone offline. And we need to be able to do advanced scenarios like, failover pools, like a kind of D3 understudy style scenario. But it's all part and parcel of the same thing. Okay, accuracy. We want our data to be communicated in the native form that it exists in. We don't want to have to turn it into 8-bit values. We don't want to have to allow the limitations of what data can be sent on the wire of the protocol to determine how we actually transport it between devices. We want native data. If it's an array, we want to send an array. We don't want to have to make 4 parameters. We need to have data that could be a variable length array. We want to be able to send data that is in different units, and we want to be able to understand what those units are. And we want to be able to convert automatically between those units if necessary, so that it doesn't matter if one device speaks in millimeters and the other speaks in meters. They can understand the implicit relationship between those values. So by sending the native data, it allows the system to have an actual awareness of what that data is and make intelligent decisions based upon it. Also important, really important for things like color and color spaces. We can actually think about having color parameters on different devices and applying the appropriate color space transforms between them. Okay, another thing for data accuracy, we want to differentiate between stateful and imperative data. Now, this is something that's kind of, we have nearly all our protocols essentially are about imperative data. The only ones that are not, I'd say, is something like DMX, where we're just persistently sending a set of values, so it is purely stateful. But like an OSC packet, for example, if we send an OSC message, that's an imperative message. It gets sent once. We are kind of understanding in the way we design a system that value then might be setting the state of something, but the network layer has no awareness of that. So how do we deal with the concept of we're sending a device, and either the sending device or the receiving device might get disconnected. So we could do it by either just constantly sending the OSC message over and over again when it hasn't changed, and how fast do we want to do that? If we do it so fast at the kind of frame rate to avoid any kind of delay, we're flooding the network with loads of unnecessary data. If we don't do that, then we're potentially incurring a sync delay if either of those devices goes offline before it gets to the right state again. So we need to understand the difference between a stateful data and imperative data, because stateful data needs to be kept in sync, and we need to know whether it is in sync or not. Okay, and finally, to address the issue of timing, we need to have an understanding of synchronization, timing, latency. And the obvious solution for that is the one that like other systems are already using since 2010 is an awareness of PTP level synchronization. So every device connected to the control network can be synchronized with a reference point and has an understanding of that. There are some protocols that already can like have an awareness of timing. So OSC has a concept of like a time tag. POSI StageNet has like timestamps. The problem with this, however, is there's no standard for like what that actually means. You can carry the information in the packet, but there's no there's no requirement on the sender or the receiver to lock that to anything specific. The only thing it's good for is comparing the difference between different messages. So that doesn't help you when you're trying to coordinate timing on the system as a whole. Next category of efficiency. So this is, by this I'm mostly talking about like network level efficiency, so to avoid we're making the best use of the bandwidth and the resources we have available. So we want to define our connections as relationships rather than as network routes. This kind of ties into the whole not using IP addresses category again. We want to define relationships between the resources we have on the system as that, rather than as sets of messages that we send from one point to another. We want to say, like, here are two, here is a value, here is a parameter that both exist on the control network and they are related intrinsically, and then let the system work out how to keep those two things in sync. So we're not defining messages, we're defining relationships. We want to ensure that the data only traverses the network when necessary. So we only send changes. We have, if we have a reliable transport, we can know when values haven't arrived and resend them. And if it's unreliable, if we nominate that data can travel by an unreliable method, then we don't care anyway. But this way, we can cut down on any repeated values being sent. So we're not sending like the, at an output rate of like 50 hertz when no data is changing. So mostly this efficiency in this case is kind of reducing the requirement for network traffic. Most control networks, I think, it's not a significant part of network bandwidth. I mean, as our systems get bigger and we're dealing with more parameters, we kind of have to start thinking about that. But I think it's still you'd have to be doing something pretty huge before you start to run into bandwidth issues. However, it's not just necessarily about that. If you're dealing with like low-level devices, then most of which are still 1000 megabit because those are the affordable Ethernet controllers that manufacturers are putting in their devices. And it's also about like the bandwidth is obviously limited with them, but also because they're low-level devices, there's an inherent processing overhead. So if you're trying to address a resource-constrained device with a ton of data, even though you may be able to carry it on the network and via the bandwidth, the chip in that device might not actually be able to process that all in time. And this is where the next point comes in is optional metadata. By metadata, I'm mostly talking about labels. Labels for systems that are mainly there to tell the human users of that system what things are and identify them. Some protocols have this and some don't, but nothing at the moment differentiates between devices that want to send and receive those or not. And for a lot of devices, ones that don't have any kind of visible user interface, they don't have no requirement for that data. So we shouldn't send it where it's not necessary. So metadata should be truly optional. On to security. Andy Bobin kind of brought this up, and we ended up talking about it quite a bit tomorrow. But yeah, I very much agree. It's like, we're very complacent about security in this industry. So I think our next generation protocol needs to be encrypted by default. You should be able to disable it, because there is an overhead involved. And again, especially with resource constrained devices, it's not nothing to decrypt packets. However, if we want to be serious about the culture towards security in this sector, I think we need secure to be the default option, and it should be disabled where necessary, rather than an assumption that like you turn it on if you need it. We want to have an actual understanding of authentication, authorization, and permissions. We shouldn't assume that every device that's connected to the control network is able to do anything to any other device. We need to have an understanding of privileges and different levels. And again, back to the example of like trying to connect like a whole bunch of Wi-Fi devices, maybe controlled by the audience. You don't want them to you may want to connect them to the control network potentially to do something interesting or interactive, but you don't want them to have the privileges to address anything else on the system. You may want to look at data that they own from the widest network, but not the other way around. So by having a privileged system and being aware of permissions, we can start to do things like that. Okay, that's all my categories. Now the question, why doesn't this already exist? I mean, like, none of these things I've talked about have been technologically impossible for, even in like the last, kind of 15 years. None of this is like kind of groundbreaking stuff. Here's my theory why it doesn't exist. Again, similar topic to what Andy brought up yesterday. It's complexity. In all the time I've been looking at this sector and looking at the various solutions, the reason the simple things succeed is because they're simple. The problem is, um, uh, I mean, like I've mainly talked about protocols that have open standards. There's also a ton of very manufacturer-specific ones. The problem with the open standards, however, is that they have to be simple because, as I've learned, as soon as you have a complex open standard, you just invite avenues for people misinterpreting it. So when I was at Hippo, I spent quite a long time working on the implementation of CITP, which is a mechanism for synchronizing metadata with lighted consoles and visualizers. Um, the issue I had with that was as I went around the various third parties that were implementing it, there was a very long, reasonably good spec document written on the protocol. Every single person had implemented it in a slightly different way because, like, the more different packet definitions and message definitions you create, the more ambiguity there is. And the only way I managed to get things to work in the end was to write like an open implementation that is now the thing that I think Hippo still uses it, I believe. I think Vertex uses it now as well. And I spent a long time then like creating that reference implementation, so I had something to give to the lighting console manufacturers to say, please test against this. But then that's an imperfect solution. If you have a like standards document that no one can, without reference to a single implementation, can implement, then what good is the standards document? So therefore, I don't think we can actually make a complex standard. So therefore, I don't think we should try and make a complex standard. What we should actually make is an implementation. And with Seismic, that's what we're actually trying to do. And our one is called Mica, which is not an acronym. So we want Mica to become the base of next generation control technology. It's not a standards document, it's an SDK, it's an implementation. It's really simple to implement in software. We eventually want to be able to have a hardware implementation level as well. And we can maintain a complex communication standard this way that can give a good user experience. But we can also know that every device on the network is going to implement it in the same way because it's running the code that we wrote. So we're cutting out any issues of incompatibilities between different devices, and we're providing like a common control plane, a common layer for devices to talk to each other without any ambiguities. So Mica's designed to cover all the features I previously talked about, but there's an extra level to it as well, which is something I would call meta control. So how I describe this is to say, like, a lot of our systems are based on requirements which were previously defined by hardware and by very fixed parameters. Like we had things with static capabilities, so the control layer only had to do a set amount of things, and that wouldn't change over the course of the production. I don't think that's really true anymore, like because especially in video, so much of our systems are based around software where the requirements can change in the blink of an eye. If we're talking about anything like Unreal or Notch-based, the difference between having one parameter and having 10,000, you can do that in a second. And so currently the mechanism for that is you either have to massively overspec the things, your control requirements and what you're going to need, or you have to just constantly reconfigure your system. And this is what I think we need to get away from. So what I define as meta control is the ability of the control system to cope with changes to the configuration and resolve those in an automatic way without human intervention. So the things that enable that: data sharing and querying. So here I'm really talking about non-real-time data. In Mica, any device can declare a resource called a table. What this actually is a full SQL database table, which can contain completely arbitrary data. And this gives you an API for, an IPO would be nice. An API for cross-device data sharing, cross-product data sharing in a way which allows really rich communication between devices that don't have to know anything about each other in advance. So, for example, media servers could publish their content libraries. Lighting Desk can publish their queue lists. Any device can publish its entire configuration for inspection by the network, and then we can take those values and use them to influence different parts of the control system, even at the real-time layer. So why is this better than just like, accessing this same content via like an existing HTTP API, for example? Because we're a real-time system, we can get push notifications when things change. So devices can register to watch the tables and perform queries on the tables of other devices. These can be kind of standard SQL queries, or can just be built from like simple kind of requirements for people that don't want to write an SQL query. We can also create complex queries that incorporate tables of multiple different devices, and republish those as like derived tables, and then still get the push notifications from them. So, for example, we could create a real-time updating list of every queue in a show that used a particular media asset, or a table that cross-references like the sizes of the LED surfaces in our media server project with the sizes of those surfaces as they actually exist on the processors, and give us notifications when they were out of date. So this isn't real-time data, but what makes it the real-time element of it is because the meta of it is we want to know when things change, and this gives us a mechanism that's independent of any one product or platform to understand that. Finally, we want to be able to define expressions and relationships at a network level. So this is again about creating connections between resources rather than connections between IPs and devices. But we can take that one step further. Rather than just saying that this value is equal to this value, we can apply expressions of that. So we can say that this value is the result of a calculation between two other values on the network. So for something like a tracking scenario where we wanted to, say the position of this element is a calculation based on the position of this tracker, if it exists, plus an offset if it exists. And we can also reference both the real-time and the non-real-time data in those expressions. So we can create systems that are really resilient to change because they are based on variables that can be reported and updated in real time. Cool. So our goals for Mica is to become the preferred control layer for rich communication between software and hardware. We want to offer a way to break through the restrictions of existing systems, enable some new product categories. We're using it as the core of our Granite show control products, and in some other software we're making. But the value of it comes through wider adoption by the industry. So it's based on a server-client architecture, so there's a server process and the client process. The client process is what actually needs to be implemented in hardware and software products. That's a fully cross-platform SDK, and it's free to implement as a client. We're going for like kind of NDI type model where it's not necessarily like an open source project. We're going to be maintaining it. We're going to be managing the code base, but the actual implementation for devices is royalty free. We've got our eyes on hardware development kit for the future. But obviously for now, we have minimal implementations in anything outside of our products. We are writing plugins for environments which support third-party plugins like Unreal, Touch Designer, other systems like that. But for connecting to current devices, in order to currently do something useful, we have another software tool which will be released in the next few months called Mica Bridge. And what this is an environment that allows you to take an existing device, whether using like a proprietary API or an open standard protocol, and connect it into the Mica system. You don't get all the advantages of being a native Mica device, but it enables you to start using things and thinking in this way, start understanding the advantages of addressing things in this manner, and then hopefully as we can move towards native integrations in most devices, then the use of this tool will become less. But it's important for now. So if you're interested in the Mica SDK, I have a QR code here to scan to leave your details. The aim with the SDK is we'll start sharing it with select third parties in the next few months. But we're really interested to see what we can achieve with a kind of new approach to control. So thank you very much. Hey.
I know just enough about engineering and development, as you know, to be very dangerous, right? So is Mica a sort of a standard that's going to carry both control data and signal data? Well, differentiate, like would SP2110, for instance, be a kind of the data that would be carried on
No,
as
it is
opposed to SACN?
it is purely for control.
Got it.
Yeah, like signal level stuff, which obviously like the transport of like actual video and audio data. And even to the extent like if you were like, you know, addressing a whole heap of lighting fixtures by something like SACN, which is more of a video signal really than a control signal at that
Yeah.
point, arguably. We're not like, that's like kind of slightly out of scope. We're not trying to become a universal transport for all types of data. We're very much focused on the kind of the values you use to drive those systems more than the actual signal output.
So in that case, with like SACN, it'd be more like an RDF layer, where it's like the talk back from the.
Yeah, it'd be like the you know we're like hoping to kind of offer an alternative to DMX for certain avenues, but like I'd say at the level of yeah, at the level of SACM where you're just addressing like, you know, pixels or pixel tape or stuff like that, it's what you're really you're just sending RGB values, so it might as well be a video signal. It's probably only being sent by DMX because the fixtures you're using only have DMX inputs.
I think you have two questions, but the first is, so you alluded to the connection versus connectionless TCP well, you point to have both. Are you sort of envisioning like sort of like FTP did back in the day, where you got like a connected layer for managing the connection, and then like a UDP layer for raw like high bandwidth data transmission?
Essentially, yes. However, like, so Mica is kind of transport agnostic, and then we can plug different network transports into it. But where supported, the default one is something called QUIC, which is the technology that's at the base of HTTP3. What that is a UDP-based connection protocols. A lot of the way we've designed the networking stack for Mica is based on technologies that, like looking for what are other scenarios in other industries which need to transport huge amounts of data where latency is really important. They need to understand what the latency is as well. And can't like are not using things like TCP. And the answer was actually large-scale multiplayer games. So our like network stack for that is very heavily based on the kind of patterns they use, and the connection-based UDP connections is something that's like the sort of standard way that in gaming the things have been done for a long time. So it's a natural kind of fit for this application as well.
The other question was, so you talk about MDNS to zero style of configuration, and you alluded a couple of times to NDI. So I guess like the zero conf routing that NDI does has been kind of shown to be in practice sometimes problematic in terms of finding the optimal route between two points. Like, is there any potential to have some sort of, as part of your meta configuration, the ability to inspect the sort of solution that has been arrived at by the MDNS component, so that you can debug potentials?
Yeah, absolutely. What the discovery layer will tell you, if you like, I mean, depending on how much you want to get in the middle of it, you can just say, just try and discover the server and use whatever route you can. You can specify what adapters it can and can't use, which is something that NDI can't do, which is the main issue that people have with it. So you can kind of get in the middle of that and try and negotiate a connection and say, okay, I have found the server with these available routes, and then allow the user to select the one they want to use, or select more than one if they want something that's more resilient, or they want to share the bandwidth between the different connections.
And so in this ecosystem running this protocol, you would have a server as that discovery, as that.
Yeah.
Yeah.
It's so the logic of the server client structure is basically that in order to keep the clients as dumb as possible and make sure they can run on resource constrained devices, we do all the intelligent stuff on the server. And that's also what allows us to manage the I/O to all the individual clients and manage the relationships between them, because by having a server, we've got a sole source of truth. So we can say, one device can say, I want this value to be the value of this other thing that exists on the system. That device itself never needs to receive that value because the server already knows it, so we can negotiate that transaction. So the requirement of the server is you need to run it on something that's like not, you know, a lemon. It needs to be like a reasonably capable PC, although it doesn't have a particularly high system requirement. But that can be one of the devices in your network which is doing something else anyway. Yeah.
So
Mhm.
it's not like you're not gonna sell hardware like a server, I mean, I don't know.
Yeah, so our Granite product contains a built-in Mica server and is the kind of management layer of that. Mica Bridge will have the option to run a server as part of it, or it can connect to a server externally. And we will eventually offer like a standalone server software with for like integrations in certain custom scenarios.
But in theory, like, I'll be able to just download it on my PC, like, server, control server, and then my kind of devices and all that.
Absolutely, yeah.
On the expression layer of the network that you described, do you have any like key examples that you think about? Because I think that, to me, out of everything you talked about, is like the most exponential gain for the entire production stack.
Mhm.
Right, because every single department, every single modality within the production can take advantage of that. Because that whole system can react and.
Yeah.
Like,
And that's a really good word actually. That is the idea of reactive systems and because expressions I think give us a link into thinking about rather than about this sends this message and this receives this message and having to think about when that happens. We are defining our relationships more as kind of links that we don't have to interrogate about the specific timing of when the communication happens. We're just saying there is a relationship between these two things. And expressions are a great way of, whilst you can create that relationship without an expression, the expression that makes that vastly more powerful because you incorporate other sources of data. And again, this bit I was going to talk about on the previous slide. There have been attempts to make something like this as a standard. So everyone knows SACN. Has everyone heard of ACN? SACN was the compatibility layer for ACN, which was supposed to be the next generation protocol. No traction. No one did anything with it because there was no reference implementation. It was very complicated, and it's primarily targeting the lighting industry, which has a very real impetus to change because it's like a chicken and egg scenario. Who's going to do it first, the fixtures or the consoles? So, like we're trying to with like everything about this and the design, the way it's designed has been focused on trying to get the adoption up because that's the only way it's going to succeed. Is we have to get and we realize that like we're asking a fair amount from software and hardware implementers because for this to work properly and provide possibilities, it has to reach quite far into the software to expose things that maybe previously aren't even exposed at the moment. However, by doing it as an implementation, we've done most of the work in terms of the actual kind of socket level and all the network communication, and we've tried to make the API as simple as possible. We're working on bindings for various languages. By core, it's a C API, but we're also using it in a C# form because that's some of our other products are written in that language. We're open to creating other wrappers as different third parties need them. We want to make the implementation of this no-brainer because we want to provide so much functionality for people to implement it that it's easier to just implement our protocol and our SDK rather than making these features themselves.
Have you put any, has it come up with any forwards backwards compatibility, or is it just like Mica is set and
So I think obviously that is a concern as we want to evolve the protocol, and I think again being an implementation rather than a standards document helps a lot because we can generally keep the API basically the same. That's one of the really nice things about the NDI API, by the way, is that you can as they add new features, the API stays compatible, which is why you can load a completely different version of the NDI runtime into any application that's implemented it because they never deprecate stuff in a way that would make your application crash. We're aiming for the same kind of thing. We can add new features. We can change the way change all the way that the messages work without changing the way it's actually implemented in the software. Obviously, we need to have a layer that manages the kind of versioning at a network layer. But again, because we've got a server process, we can handle that. So say we've got like server version 2, and there can still be clients that are on client version 1, but because the server can still speak client version 1, we can actually have devices where there have different versions and implementations of Mica because they're all transacting via the central point, which is intelligent enough to understand multiple versions of the protocol.
Is this like layer 5? Something? Can you cross routers and things?
It could if you configured it that way. Like there's a concept not yet implemented that you can create connections between servers to bridge, like for example, bridging two sites that you wanted to connect via the internet. Where again, it then kind of is just a bit more intelligent about it works, like which data needs to traverse from one side of the connection to the other. So that would be a way to get like through a kind of routing barrier. Yeah.
So I guess like an implementation that I see, and like tell me if I'm wrong, because like I have a disguise server, I have a Panasonic projector. We like to do laser fade and shutter controls. So you know, if the disguise server will query the projector and say like, okay, I want to see what I can control on you, and then it'll like essentially the whole be it opens up that list on the server that can essentially keyframe that.
Yeah, pretty much. That's kind of what I imagine an implementation disguise would look like. Is like similar to the way the notch layer works, in a sense of you like pick a thing that you want to connect to, and then it will like automatically populate the list of parameters for that layer module with the things that exist on the network, and then you can start to attach keyframing data to it.
And then, like, we have the server, so it would query the server, what it would have, and then the server would tell it, or essentially the server would say these two things can connect, and then those two things connect without the server.
Yeah, so we have like the clients can identify different kind of resources. One of which being a parameter, which is a way of saying, hey, this is something which is externally controllable. So from a disguise layer perspective, that's what you're interested in. You're not interested in sources of data, only kind of destinations. So yeah, everything transacts via the server. Generally, the clients don't talk to each other, except where that is efficient for a network data purpose. The server can deal with the concept of, like, I've got 10 devices that all need to receive the same data, so it would be better off to multicast it rather than send it individually to all devices. However, that's a managed process by the server. The clients can't opt for that explicitly. It's done and changed and in real time. So yes, the client asks the server what resources exist, what devices exist, and you can choose from that list. The other thing that advantage they have is that like resources can have different lifetimes. So if like you've connected your projector, it's been on the network, it's registered the parameters it has with the server, and then it goes offline, those items still remain on the server in the discovery table. So you can still create that connection even if the projector is powered off or is not online at that time.
Is there an issue of stale data?
Yes. It's like there is attached to every kind of resource, like a parameter or a variable, there is a feedback system to say what for parameters there's a couple. There's a status to say whether the value it has is up to date or is unlike, we've lost sync at some point or we don't know what the value is, so that we can intelligently reason about what to do in that scenario. Also with a parameter, there's a concept of feedback where you can say what the value actually is. Because like with things like, for example, an automation system, you might be able to tell a motor to move to a position that it can't physically do because someone's pressed the e-stop or because something's blocking it. So you can report back the difference between the value that is being sent by the control network and where the thing actually is in real time.
With that, we do have to wrap up, but how about this last question, and then we wrap, that's Easter.
Just how I watched colleagues try to evolve quick video for quick. I can see how hard it is, even with an open protocol and an open reference implementation. NDI seems like an engine pattern in getting us going across a lot of platforms. Are you open to opening up the server implementation to get more deeply embedded into like quick and video quick?
I'm not necessarily against the opening up some sections of the protocol. What my concern is, and what we're trying to protect against, is we don't want, as I say, this succeeds through adoption, but it also succeeds through everyone using the same standard. I don't want to create a scenario whereby we open it up and individual manufacturers go look at, the way that things are being done and just adopt the pieces that they want to then make their own implementation that only works with their products, because that is counter the whole effort. So it's like there's a level of IP protection obviously for us, especially in like the kind of the way the server side is working. But like it's kind of I don't see uh, I don't see it necessary for the manufacturers to need to have an understanding of the low level, except where it's necessary for their engineering, and we can work with them to illuminate those requirements where necessary. Mhm.
You had talked about previously licensing servers.
Mhm.
So you would take an enclosed server, not knowing where these, you'd be able to in software, Jasper Media Server. So you could host the server yourself without having to buy potentially a server from us. It's asterisk.